Welcome to aminacademy.com. In astronomy, let us discuss about Doppler effect. Astronomers can learn about the elements in stars and galaxies by decoding the information in their spectral lines. There is a complicating factor in learning how to decode the message of starlight. However, if a star is moving towards or away from us, its line will be in slightly different space in the spectrum from where they would be in a star at rest. And most objects in the universe do have some motion relative to the sun. This information is explained by Doppler effect. Motion affects waves. In 1842, Christian Doppler first measured the effect of motion on waves by hiring a group of musicians to play on an open railroad car as it was moving along the track. He then applied what he learned to all waves, including light, and pointed out that if a light source is approaching or receding from the observer, the light waves will be respectively crowded more closely together or spread out. In general, principles now known as the Doppler effect. You may hear a Doppler effect with sound waves when a train whistles or police siren approaches you and then moves away. You will notice a decrease in the pitch, which is how human senses interpret sound waves frequency of the sound waves. Compared to the waves at rest, they have changed from slightly more frequent when coming towards you to slightly less frequent when moving away from you. Color shifts. When the source of waves moves towards you, the wavelength decreases a bit. If then waves involved are visible light, then the colors of the light changes slightly. As wavelengths decreases, they shift towards the blue end of the spectrum. Astronomers call this a blue shift. Since the end of the spectrum is really violet, the term should probably be violet shift, but blue is a more common color. When the source moves away from you and the wavelength gets longer, we call the change in colors a redshift. Because the Doppler effect was first used with visible light in astronomy, in terms of blue shift and redshift became well established. Today, astronomers use these two words to describe a change in the wavelength of radio waves or X-rays as comfortably as they use them to describe changes in visible light. The greater the motion towards or away from us, the greater the Doppler shift. If the relative motion is entirely along the line of sight, the formula for the Doppler shift of the light is delta lambda by lambda equal to V over C, where lambda is the wavelength emitted by the source, delta lambda is the difference between lambda and the wavelength measured by the observer. C is the speed of light and V is the relative speed of the observer and the source in the line of sight. Now let us discuss further about Doppler effect in astronomy. In astronomy, Doppler effect describes how the frequency of light waves from the moving source like a star or galaxy appears to change to an observer, shifting towards blue or approaching sources, blue shift, and towards red for receding sources, red shift. Look at this figure. Here, the shifts, color shifts are shown. What is the Doppler effect? A Doppler effect, also known as the Doppler shift, is a phenomenon where the frequency of a wave like sound or light appears to change from an observer who is moving relative to the source of the wave. How it works in astronomy. Blue shift. When a star or galaxy is moving towards us, a light waves emitted by it appear to be compressed, resulting in a shorter wavelength. and a shift towards the blue end of the spectrum. Redshift. Conversely, when a star or galaxy is moving away from us, the light waves appears to be stretched, resulting in a longer wavelength and a shift towards the red end of the spectrum. How it is used in astronomy. Measuring radial velocity. Astronomers use the Doppler effect to measure the radial velocity of stars and galaxies, which is the speed at which they are moving towards or away from us. Detecting binary stars. Doppler effects can also be used to detect if a star that appears single is actually part of a binary star system as the stars orbit each other, causing a wobble in the spectrum of the primary star. Measuring rotational speed. Doppler effect can also be used to measure the rotational speed of stars and galaxies. For example, sound. A classic example is the change in the pitch of a siren as an ambulance passes by, sounding higher as it approaches and lower as it moves away. Light, for example, in light, the Doppler effect is used to measure the speed of stars and galaxies by analyzing the shift in the wavelength of their emitted light. Doppler effect as a color shift. The Doppler effect describes the change in frequency and therefore color of a wave like light as a source moves relative to an observer, resulting in a blue shift when the source moves towards the observer and a red shift when it moves away. Here is more detail about the Doppler effect. This phenomenon occurs any wave including a sound, a light, and is the change in frequency observed when the source and observer are in relative motion. Already we talked about red shift and blue shift. What is red shift here? When a light source moves away from an observer, the light waves are stretched, resulting in a shift towards the longer wavelength, red end at the spectrum. Blue shift. Conversely, when a light source moves towards an observer, the light waves are compressed, resulting in shift towards the shorter wavelengths, blue end of the spectrum. Astronomers use the Doppler effect to measure the speed at which the stars and galaxies are approaching or receding from us, helping them understand the universe's expansion. Imagine a car approaching you with its siren blaring. The sound waves are compressed as the car moves towards you, making the pitch higher, the blue shift in sound. As the car moves away, the sound waves are stretched, makes the pitch lower, red shift more in sound. So far we discussed about Doppler effect used in studies of astronomy. We have done. Please subscribe our YouTube channel.